Hello everyone. Today we will discuss the design and implementation of real-time systems for IoT devices. The members of our group are Ana Marínez, Humberto Frenier, Alberto Martinez, and Patricia Secas. Alright, so today we will cover the introduction of the real-time systems. We will give a little background of the Internet of Things. We will discuss the operating systems in the real-time systems through the types, the architecture, its features and its limitations, and then we will talk about how they both go hand in hand by discussing their general architecture, their vision, some of their challenges, and the requirements that they need to meet. And we will follow up with the conclusion. Introduction. Real-time systems are found in the Internet of Things around the world primarily to serve a specific function. From home appliances to traffic lights, real-time systems are necessary to perform tasks that should be guaranteed within a specified timing constraint in order to meet a specific deadline. These systems are designed to meet a certain deadline in order to prevent catastrophic events from occurring. The operating system in an IoT device differs from a personal computer in the way that they are less complex and do not require many of the same resources to execute its main function. The features found in the real-time systems help build an infrastructure of connected devices that greatly impact society, as demonstrated through its design and implementation. Now, Patricia will begin presenting the Internet of Things.
Thank you, Alberto. Internet of Things, introduction. A simple concept that we have for Internet of Things is basically connecting any device with an on and off switch to the Internet, or these devices can be connected to each other. This includes everything from cell phones, coffee makers, washing machines, headphones, lamps, wearable devices, and almost anything you can think of. This also includes components of machines, for example, a jet engine of an airplane or a drill of an oil rig. To make IoT work, you need a unique identifier network access and a device or sensor to transmit data, and that's it. The background for Internet of Things. The concept of Internet of Things has been around since the early 90s, and it had to do more with the RFID technology, which is the radio frequency ID communications, which has been used since the mid 80s, which is a kind of old technology, with people taking advantage of RFID and different kinds of passive and active devices. Nowadays, we find more and more devices, such as cell phones, connected to the internet. The connection to the internet can be directly, could be wirelessly, or by chip. IoT was first mentioned by Kevin Ashton, the co-founder and executive director of the Auto ID Center at MIT. He publicly spoke about it in 1999. And now, after 18 years, more devices are coming online and ideas continue to flow to create the interconnected world. A report from McKinsey Global Institute states that Internet of Things impact will reach a 2.7 to 6.2 trillion dollars annually by 2025. Different companies got different reports on how many IoT devices will be connected. For example, Gartner estimates 26 billion devices, and Cisco 30 billion of IoT devices will be connected in the near future. This will help businesses to learn more about the consumers to provide more services. With the amount of information available traveling the networks for consumers, these become a privacy issue. We are at a time that we do not have much privacy. When signing up on a web page for a service, for example, we users are not reviewing the terms of service, and this way we are giving up on our privacy. It is important to mention that privacy laws are different in every country. For example, in the United States, you don't have access to change the information once it's part of public records. But in other countries, like in Europe, in the European Union, for example, consumers do have that control on their personal data. So how the IT leaders can be prepared for IoT? This was an online report from eWeek by tech journalist Jeffrey Burt discussing this important subject, suggesting IT leaders to take action about their Internet of Things preparation. The recommendations are: be part of early planning for Internet of Things deployment before any buying decisions are made. The second one is rework network access policies to ensure that new devices and systems connecting don't endanger network resources or security. Another recommendation is ensure network tasks are automated when possible. And the last but not least is the deploy of the IPv6 IP addresses on IPv6 plans to ensure that the shortest on the IPv4 addresses don't slow down their efforts around IoT. So let's talk about the IoT technology stack. The IoT technology stack is divided in 5 layers, and these help better to understand the IoT technology. The layers are, the first one we find the hardware. They are different, they are the interface between the real and the digital world. The goal of IoT hardware device is just to collect data. Depending if we are talking about a small or industrial device, then the systems are very different. For example, for a smartwatch, a simple chip SoC is enough, but for more demanding solution, you might need an embedded computer like a Raspberry Pi. Then if we are talking more serious computer needs, an advanced industrial computer like a PXI must be used. Hardware is also need to communicate the data up to the cloud. As a second layer, we find the software. The device software is the part that turns the device hardware into a smart device. Device software will be developed by software engineers. The device software allows you to communicate with the cloud or to other local devices. This part of IoT stack is extremely important because it serves as the glue between the real world, which is the hardware, and your cloud applications. Building hardware is very expensive, as we know, and it takes a lot longer than create software. So it is better to use generic hardware and then customize it with the software. The third layer is the communications. Communications is a reference to all different ways that the device will exchange information with the rest of the world. This includes both physical networks and the protocols you will use. Communications are tied to the hardware and software, but it is worth thinking of these as different layers. Choosing the communication mechanism will determine how will your device communicate with the cloud, meaning Wi-Fi, could be LAN, could be the WAN, etc. And also how we'll communicate with other devices. Cloud platform. This is the backbone of the IT solution. This is what we call software as a service type of platform. This layer will serve for data collection and management analytics and cloud's APIs. The last one is the cloud applications. These are your end user applications. They are part of the system that customers and users will see and interact with. Usually, they are web-based, or and depending on your user needs, you might have separate applications for desktop, mobile, and even wearables. Applications can also be divided into customer-facing versus internal applications. Customer-facing applications usually get the most attention, but in the case of IoT, internal applications are equally important. And now I'm going to leave you with Anna, and she's going to talk about the real-time operating system.
Thank you, Patricia. So in this section, I am going to talk about the real-time operating system. If you could please pass to the other slide. Thank you. So real-time operating systems is a computer system that must satisfy well-defined time constraints or risk failure. In other words, real-time systems work correctly when they can execute its functions properly within the specified periods of time at which the results must be given. If the system is not able to execute within the time constraint, then its function fails. RTOS, or real-time operating system, supply many valuable roles to an embedded system, but the main purpose of this software is to serve the scheduling of the CPU. The scheduling that this operating system must serve are those of tasks. Any given application is structured by processes which have their own program code and require the use of registry and memory values. These processors are combined to perform tasks, which are just a set of processes with data dependencies. Each task and/or processes have constraints that must be triggered for the application to perform as desired. Usually, they will have deadlines, which is just the time in which a process must finish its execution after it was initiated. As mentioned, real-time systems are defined by time constraints, bounded by the deadline set of the application's tasks or processes. So it is the job of the real-time operating system to serve the CPU as efficient as possible to meet those deadlines. RTOS can be classified in two main categories: hard and soft and firm real-time operating system. Hard real-time operating system, just as hard real-time system, consists of operating systems that must adhere to deadlines imposed by the task that applications have. If a single task fails to meet a deadline, the results may lead to complete system failure. An example of this is the brake system of an automobile. Then we have firm real-time operating system. This real-time operating system can miss a few deadlines, but missing more than set few can lead to system failure. Example of this include food processing plant control systems and streaming audio video. Then we have soft real-time operating system, a system which performance is degraded if its function is not performed within the specified response time requirements, but it does not result in a system failure. Example of soft real-time systems are video games, cell phones, or seismic sensors. Real-time operating systems, just as any operating system, are comprised of multiple components, such as the kernel, process execution, interrupt, memory management, multitasking, networking, security, and user interface. However, in a high-level overview, an operating system consists of two main parts, the kernel space and the user space. RTOS commonly only includes a kernel, but they can include more components depending on the complexity of the embedded system. The kernel is a fundamental part of the operating system. It's what acts as a bridge between applications and data being processed at the hardware level. There are different types of kernels typically used in RTOS. One is the monolithic kernel. The kernel covers all the components in a system that includes hardware, IPC, which is inter-process communication, file system, drivers, CPU processing, etc. The systems are highly effective on devices of single processors since it does not need many context switches, which is the procedure when a CPU changes between tasks or processes without conflict. Then we have microkernels, which only supports the fundamental but basic parts of the operating system. Then we have a hybrid kernel, which are a type of microkernels with some functions of monolithic kernel, and exokernel, which only run on services safeguarding hardware resources by providing low-level interface for library operating systems and leaving the management to the applications. Task management, another component, is a critical component for real-time operating system. As mentioned, tasks are the decomposed, schedulable, and sequential process that form an application. Tasks are ruled by three time critical components: release, deadline, and execution time. When an application is executing, individual tasks are concurrently changing state. However, only one task can be run at a time. In the meantime, context switching happens to the CPU to interchange between tasks. Scheduling algorithms are crucial as well for real-time operating systems since they have a great impact on runtime performance. The algorithm consists of different variables from an application task and schedule their execution and states to maximize runtime. Issues such as multitasking and task priority are addressed by these scheduling algorithms. You have different types of algorithms, such as cooperative scheduler, static priority-driven scheduler, and in which you can find the rate monotonic scheduling. You have dynamic priority-driven scheduler, in which you can find the earliest deadline first algorithms, and you have round robin. Another component are task synchronization and communication, which are fundamentals for tasks that share mutually exclusive resources, such as buffers, devices, and allows for concurrency execution between tasks. Then you have inter-process communications, or RPC. On the other hand, that refers to the mechanisms for real-time operating system uses to allow for tasks and processes to manage shared data. Lastly, the components that we mentioned are memory, timer, and input and output management. Memory management includes services for fluctuations, deletions, and protections. And then you have, for input and output devices, RTOS handles input and output for handling subroutines such as read-write for peripheral devices. Also, to keep track of task delays, timers that are relative or absolute are provided in real-time operating systems. RTOS also have limitations and very good features. One of RTOS' main features is the capability to reduce jitter, which happens when there's a delay between the time a task is set to invoke and is set to release. When designing a real-time operating system, the focus should be to create a software that allows of rich feature sets for development and deployment without compromising on deadlines and predictability. Therefore, features that must be included in RTOS are task priority, which permits the preemption to identify and allocate resources to tasks that it needs the most, reliable inter-process communications that allow for multiple tasks to communicate and ensure data integrity with each other, and you also have avoidance and handling of deadlocks. Others are memory footprint and runtime performance, which is the reduction and avoidance of jitter, latency, and worst-case response time. The well-known limitations of RTOS is that they can be costly, as are general complex systems that can consume a vast amount of processor cycles and do not support multitasking without the use of round-robin scheduling. Also, limited tasks can run at the same time, meaning that the processor's focus can only be placed in a few applications at a time to avoid failures and waiting time from other tasks. Now, I'm going to give chance to Humberto so he can talk about real-time operating system and IoT devices.
Thank you, Anita. IoT involves extending internet connectivity beyond standard devices, such as laptops, desktops, smartphones, and tablets. Embedded with technology, these devices can communicate and interact over the internet, and they can be remotely monitored and controlled. IoT devices have many challenges, such as security risk, system development costs, power reduction, product building flexibility, and huge number, as Patricia mentioned, of connected devices. These challenges raise a lot of requirements which must be handled by the RTOS. Scalability can create an incentive for manufacturers of embedded devices to maintain a broader product portfolio. A single RTOS that can scale to meet the unique memory footprint, functionality, and processing power requirements of multiple product classes that can help manufacturers of embedded systems increase the return of their operating system investment. Cut development costs also by leveraging the economies of scope and reduce time to market. Safety is a paramount in many embedded operating systems because they control machines that can endanger life, or their malfunction can cause injury or death. Although well established in aerospace, medical, and industrial markets, safety standards are now being applied by regulators to new markets. Also, better applications of existing standards to such systems as smart grid meters or medical devices are being sought. As standards evolve, manufacturers increasingly look to RTOS vendors to deliver the appropriate safety and security capabilities and certifications in order to make it easier to obtain required safety and security certifications for their end products. Cutting-edge features is a broad feature set delivered by a modern RTOS and an ecosystem of compatible third-party applications. This is essential to enable manufacturers of embedded systems to create a differentiated product offering secure and sustainable competitive advantages. Some of these features are rich user interface, custom tailored RTOS, multi-core, compatible software and hardware, and also 64-bit processing capabilities. Connectivity feature is to support many communication standards. Security is important against threats and malicious attacks. Embedded devices have traditionally been isolated, but now increasingly connected to corporate or public networks for a wide range of applications, forming the Internet of Things. Small standalone sensor devices are connected together using low-power wireless technology. Industrial control systems are interconnected and controlled remotely. Medical devices used at the home send diagnostic data back to the hospital. A reinvented RTOS for IoT needs to support industry-leading communication standards and protocols such as CAN, Bluetooth, Wi-Fi, and Ethernet, and deliver high-performance networking capabilities out of the box. Modularity. Modularity means that our system will be implemented in modules. So if we want to add new features in our smart device, it will be simple. Traditionally, RTOS systems are monolithic in nature, and historically, they have been delivered all at once as a large bundle of software, middleware, operating systems, and tools. Modern RTOS must be built on a modular, upgradable, future-proof architecture that separates the core kernel from middleware. This slide provides a general vision for RTOS on IoT. In this direction, using RTOS in implementation of the IoT, so in this direction of research, authors has proposed to use RTOS in IoT projects, implementations such as smart buildings, hospitals, agriculture, etc. Also, it has been proposed using RTOS as an IoT framework, which will provide an efficient low framework and also embedded micro application service. As well, it has been proposed to use RTOS as performance evaluation of IoT devices. Now, Alberto, I will pass the ball to Alberto, who will cover security on RTOS and IoT devices.
As mentioned previously, real-time systems are built differently from standard PCs in the way that they are less complex and are mainly optimized to minimize processing cycles and memory usage. With that said, you can see where security may not be the strongest feature in a real-time operating system. They present many challenges and have to meet certain requirements. Lack of a strong security system makes real-time systems an easy target for hackers. Challenges. We start by explaining some of the security challenges for real-time systems. The design of an embedded system does not allow for many of the security features found in personal computers to be compatible. Most of the embedded system security relies on password authentication and security protocols. This presents vulnerabilities since passwords can easily be obtained. Also, assumptions that real-time systems are not targeted by hackers leads to the low priority in having security in these real-time systems. Next, embedded systems are usually mass-produced. This means that many of the same devices have the same vulnerabilities. If a hacker can attack one device, that means he can attack many of the same devices. These devices are not fully featured and supported. Once they are produced and deployed, the systems will run on that software that was integrated from the factory. There is almost little to no support or updates that can fix any of the attacks that were implemented by a hacker. The last challenge is that the life cycles are meant to be very long. It's difficult to design something that's going to last more than 10 years since they have a simple purpose. Also, it is hard to defend against evolving attacks. Requirements. Now we move on to the requirements. With the challenges presented, it is important to meet certain requirements when implementing security on a real-time system. Security needs to be tailored to the needs of these devices and must be considered early when they're being designed. All types of communications should be authenticated to ensure that the access is controlled and provided to the correct source and destination. For example, factories build real-time systems with a master password to allow secure boot. A cryptographical signed code from the manufacturer, along with the hardware support, can verify that the handshake is authenticated. Secured coding can also allow the machine to provide the correct patching or updates. Other features such as data storage and communication can be encrypted to avoid breaching. Lastly, newer processors include the ability to detect if the enclosure of the device has been tampered with. Authentication. Now that I have mentioned some of the requirements to have a secure system, I will demonstrate how we can implement these methods, starting with authentication. Any communication between devices or nodes should have a secure method of authentication, usually through a strong password or through authentication protocols. One method is Kerberos. Kerberos is an authentication protocol that uses tickets to allow nodes to prove their identity and communicate over a secure network. Kerberos uses a symmetric key cryptography and requires a third party for authentication. The steps for authentication follow. First, a client request can authenticate a ticket from the key distribution center. The key distribution center verifies the credentials and sends back the encrypted ticket and session key. Then, the target granting ticket is encrypted using the ticket granting service. Lastly, the client stores the ticket granting ticket, and the local session manager will request another TGT when it expires. Communication. Simple network protocols can be used when communicating over the network. Secure Shell, or SSH, can be used in the application layer of the TCP/IP suite to encrypt communication. The application uses SSH to connect to the application server. With tunneling enabled, an application contacts a port on the local host that the SSH client listens on. The SSH client then forwards the application over its encrypted tunnel to the server. The server then connects to the actual application server, usually on the same machine or in the same data center as the SSH server. The application communication is then secured without having to modify the application or end user workflows. Intrusion detection. Lastly, we can implement an intrusion detection system to control the flow of the network traffic. In this example, we implement an embedded firewall through floodgate packing filtering. These firewalls help protect the flow of packets by either allowing them or blocking them from the entire network. It can allow for the network devices to control packets before they are processed to avoid malicious attacks from entering. This is based on a set of rules that the admin can create. Once the rules are set, these steps follow. First, a packet is received from the network. Dynamic filtering engine logs events and drops packets if the rules are met. If the rules don't match, static filtering engine reviews packets and determines if log events and drops packets if rules are met. If rules don't match, it will go to the next step. The threshold filtering engine reviews packets and determines if log events and drops packets if the rules are met. If rules don't match, then normal packet processing is continued. To conclude, we discussed the design and implementation of a real-time operating system. We discussed the testing methods and the uses of an RTOS in IoT devices in the present and for the future. Lastly, we discussed how to secure real-time operating systems by presenting the challenges and the requirements for security.